This morning, it's a great pleasure to introduce Ljudmila Kamenova from Stony Brook. And today, she'll talk about the Twistor space limiting both Kähler and non-Kähler structure.
Thank you very much for the introduction. It is an honor being here to celebrate Nigel Hitchin. Thank you for the invitation. So today I'll do a crash course on Twistor spaces and talk about some Twistor spaces that admit both Kähler and non-Kähler structures. This was a question by Michael Atiyah from a long time ago. So let me introduce the basic setup of Twistor spaces. So, for example, if you just fix Rn with a standard inner product and orientation, consider the space of all complex structures on R2n, which are compatible with the metric and the given orientation. So this is the compact remission symmetric space SO2n modulo UN, and is denoted by gamma n. So this space parameterizes complex structures which are compatible with this data. And the real dimension is even, it's dimension n times n minus 1. So now, locally, if you take an oriented Riemannian manifold of dimension 2n, you can patch it up by local charts that look like R2n. So you can make this construction global. So, for example, because the holonomic group of M is contained in SO2n, actually, if you have an oriented Riemannian manifold of dimension 2n, let's consider the principal SO2n bundle associated to M. And you can take the Twistor space is just the principal SO2n bundle modulo UN. So then the Twistor space or the Twistor bundle is just a vibration over n. Firstly, the fibers are this gamma n. By vibration, I mean proper homomorphic map, which is surjective with connected fibers. So then this Twistor space is the vibration over M with fibers gamma n. So it is of even dimension, and it has a tautological twisted almost complex structure. So basically, what happens is that the Riemannian connection of M determines the splitting of the tangent bundle into vertical part and horizontal part. And on the vertical part, where you have this gamma n, you can take the complex structure of the gamma n of this symmetric space. And then, because gamma n itself parameterizes almost complex structures on R2n, which is how you patch up locally the manifold. Then on the horizontal space, which is naturally identified with the tangent space of the manifold, you have this action of the point on the fiber is your complex structure. And this defines the Twistor complex structure, which is actually almost complex structure. So here is explicitly, you just have to have a splitting into a vertical and horizontal part. And Nigel already mentioned about this almost complex structure. And so the Twistor space is really the space parameterizing the space of complex structures compatible with a given metric and orientation. So from the definition, it is clear that the question of integrability of this Twistor almost complex structure only depends on the Riemannian metric. And you have this dichotomy. So if the real dimension of M is 4, you have one answer because the Weyl tensor is not irreducible. It splits into two parts, anti-self-dual and self-dual parts. But if the real dimension of the complex manifold is greater than 4, then the Weyl tensor is actually irreducible. So you expect a different answer. And you can interrupt me anytime. So if you want to ask questions. So, and here is the actual answer. This is the famous celebrated result by Atiyah, Hitchin, and Singer. When in the complex, in a real dimension 4, you have that the almost complex structure on the Twistor space is integrable, if and only if M is anti-self-dual. So the self-dual part vanishes. And in higher dimensions, you have that the Twistor almost complex structure is integrable, if and only if M is conformally flat. So it doesn't happen often, but it does happen that the almost complex structure is integrable. And then there is also a question about when is the Twistor space Kähler, and that happens not often at all. It almost never happens. And there is another famous paper by Hitchin who classifies in real dimension 4 when the Twistor space is Kähler. And this happens only when M is conformally equivalent to the complex projective space or to the sphere. So either CP2 or S4. In higher dimensions, it only happens when M is conformally equivalent to the sphere. But in real dimension 4, then it only happens if it's CP2 or S4. And this is another classical result. Marco was asking the other day when the Twistor space is Kähler, and these are the answers. And in small dimensions, you have a lot of isomorphisms between Lie groups and Lie algebras in small dimensions. So then you can classify the symmetric spaces gamma n. For example, gamma 1 is a point. So in this case, for curves or complex curves or for real two-dimensional manifolds, nothing interesting happens. The first interesting case is when you have real dimension 4 or complex dimension 2. Then gamma 2 is isomorphic to S2 or CP1. So these become the Twistor lines that Nigel was mentioning. Gamma 3 is CP3, and gamma 4 is the complex six-dimensional quadric. And then there is everything else is in higher dimensions. And here is some brief history of this problem by Sir Michael Atiyah. He asked, he was curious about when compact differentiable manifold can carry both Kähler and non-Kähler structures. And if it's simply connected, that will be another interesting question. And here's some first examples in this direction. In the 50s, Blanchard actually constructed the 6-dimensional example, which is the twistor space of T4, the torus T4, without having twistor spaces. So he constructed it explicitly, and his example is indeed the twistor space, but nobody had defined the twistor spaces, so he just did it by hand. Then Calabi's example came shortly after that, in the same direction. And Sir Michael Atiyah did the higher-dimensional examples, not only 6-dimensional examples of such manifolds, but actually examples that occur in any possible dimension, so even dimension. And he was doing things along the lines of twistor spaces, but they weren't quite twistor spaces. So if it is the twistor vibration, then the fiber is gamma n, which is S-2 2n modulo un. And Michael was doing a very similar vibration, however, for O2n modulo un. So basically, the complex structures that he was considering were compatible with the metric, but not necessarily compatible with the orientation. So they look like twistor spaces, but not quite. And again, his examples were defined way before we knew about twistor spaces. And then the first simply connected such example was done in the 80s by Vasil Tsanov, which was the twistor space of a K3 surface. So now the question is, can we construct higher examples solving this problem? And indeed, we'll just construct twistor spaces of hyperkähler manifolds, and this will generalize these examples. So let me mention about hyperkähler manifolds. It was already mentioned, but here is the definition. For n-dimensional Riemannian manifold is called hyperkähler if the holonomic group is contained in the compact symplectic group SPN, which you can define as the intersection of SP2nC with U2n. Then, using the Rambergès classification, we know that every hyperkähler manifold is scalar. It has Ricci curvature 0. And in the compact case, unlike the non-compact case, we have very few examples. In complex dimension 2, we have K3 surfaces. And then in higher dimensions, we have the classical series of examples which occur in any dimension. Hilbert schemes of K3 surfaces and their deformations, generalized Kummer varieties and their deformations. And then in complex dimension 6 and 10, we have these sporadic examples due to Kirano grading. So these are all the compact examples we know so far in hyperkähler geometry. And of course, we have a lot of non-compact hyperkähler examples that are plentiful. So from now on, let's assume that M is a hyperkähler manifold of real dimension 4n. Then by the holonomy principle, you have the imaginary quaternions act as parallel endomorphisms. So let's fix the standard basis ij and k of the imaginary quaternions. This gives you a 3-dimensional subbundle of the endomorphisms of the tangent space. And now in this bundle, let's take the unit sphere subbundle Z0. So if so, for example, if this E is spanned by I, J, and K, then it looks like some coefficient times A plus coefficient times J plus coefficient times K. And then Z0 of M is when these coefficients lie on the sphere. So A squared plus B squared plus C squared is 1. So this is called the small twistor space of M. And it's actually a subbundle of the big twistor, which we defined earlier. And not only this, but this twistor space consists of complex structures. You don't take the space of all almost complex structures. You just take complex structures compatible with a given metric and orientation. So Salomon showed that the quaternion twistor space Z0 of M, which is the small twistor space, admits a natural complex structure. So this is the same tautological almost complex structure that we defined earlier, but in this case it's integrable, so it's a complex structure. So you can define it again as before. You have a splitting into a horizontal and vertical part of tangent space. And then because the vertical part will be this here S2, which is the same as PP1, you have a natural complex structure there. And on the vertical part, you fix this complex structure. And then on the horizontal part, the point where you're at, this actually defines your complex structure on the horizontal slice. So this becomes a twistor almost complex structure, which happens to be integrable. So it is actually a complex structure. And then the small twistor space, Z0 of M, together with this complex structure, becomes a 2n+1 dimensional complex manifold. And you have the universal property that if something looks like a twistor space, then it is a twistor space. And here's the data that you need to fix for some space to be a twistor space. Well, the twistor space comes with two fibrations. You can take a fibration over CP1, and then the fibers over it will be the complex manifold M with the almost complex or complex structure coming from CP1. And there is a natural anti-holomorphic symplectic involution. On the fibers, it is just the antipodal map. And so, on the other hand, you can consider a different fibration. You can consider the projection of the small twistor space over M. So this is just a structure of double fibration. And then for every point in M, the fiber is just a twistor line. And it is a holomorphic rational curve. And one can compute the normal bundle, which is O of 1 2n times. And this holomorphic data above with the two double fibrations the anti-holomorphic symplectic involution, the Twistor lines with this specific normal bundle, this is sufficient to say that some space is a Twistor space. So this is the universal property. If you have a complex manifold with this data, this is actually a Twistor space. Okay. So if you have a hyperkähler manifold, then there exists a universal moduli space described by basic Twistor theory, because you can compute H0 with coefficients of the holomorphic tangent bundle. So because hyperkähler manifolds are also holomorphic symplectic manifolds, there exists holomorphic symplectic form sigma inside of each T0 of M. This gives you a trivialization of the canonical bundle, and also gives you an isomorphism between omega 1 and the holomorphic tangent bundle of M. So then this space is the same as H10 of M, which is trivial. So then there exists universal deformation space, which is locally patched up by open chart, which look like open spaces, like deformation spaces of M. So when you patch it up locally, you get a global moduli space, and it's unabstracted. So Fedya Bogomolov proved that the moduli space of hyperkähler manifolds is unabstracted. In general, for Calabi manifolds, this is Tian Todorov's theorem of unabstractedness. But anyway, you have very nice moduli theory of hyperkähler manifolds here. And so if you have the Twistor space B of n or Z0 of n, let's consider one of its vibration structures that goes over 51. So then, once you have this vibration structure where the fibers are hyperkähler manifold, then the base 51 gets mapped to this moduli space of hyperkähler manifold. And so, if you consider the moduli space, you have all these Twistor lines lying in there. And the interesting thing is in algebraic geometry, some people are interested in rationally connected varieties, like polar. A lot of students of Trollhemmings are interested in rationally connected varieties. What we have here is that the moduli space of hyperkähler is rationally connected by Twistor lines. It's rationally chain connected. So you can take any 2 points in the moduli space, and then you can find a chain of Twistor lines connecting X to Y. So, and then Fujiki showed that, moreover, if you take the one-dimensional subspace of the Zariski tangent space of the moduli space, which is spanned by the tangent space of the Twistor line, then this is given by the Kähler class of the given hyperkähler metric. So inside of this image, if this is your Twistor line, then the tangent space to this line is given by the 1-1 class associated to the hyperkähler metric. Okay. And so now I want to explore the what happens if you take a compact hyperkähler manifold of real dimension 4n, and then take the small Twistor space of this hyperkähler manifold. So this will produce more examples of Atiyah style, what he wanted to do, and they can occur in every single possible dimension. So I'm recovering from a cold, so I will keep my lecture very short, but here's the theorem. If you have a compact hyperkähler manifold of real dimension 4n, then the small Twistor space is simply connected compact manifold that carries both Kähler and non-Kähler complex structures. So one of the parts is very simple. So from the definition of the quaternion Twistor space, it is clear that if you take this basis I, J, and K, the unitary quaternions, then this gives you trivialization. So this space is locally is diffeomorphic to a product of complex manifolds n times P1, which is simply connected. So obviously it carries a Kähler structure. But now let's prove that the natural Twistor complex structure is not Kähler. So first, let's make the observation that there are no global holomorphic forms on the small Twistor space. The only global holomorphic form is the zero form. Well, this basically follows because we know what is the normal bundle of a Twistor line. So the normal bundle of a Twistor line is O of 1, and then you take 2n copies of it. So then the tangent space of the small Twistor space restricted to a Twistor line is just O of 2 plus 2n copies of O of 1. But then the dual of it, which is omega 1, doesn't have non-trivial sections. Okay, so now we know that there are no global holomorphic forms on Z0. So in this case, everything that occurs will be an H11. And so for a compact hyperkähler manifold, Fujiki also showed that if you take any Twistor family, so you fix the metric, then you produce a Twistor family. Then the general fiber of any Twistor family is not projective. So the general fiber is Kähler, but not projective. Okay, so now let's conclude the proof. If you assume that the Twistor space of M, the small Twistor space of M, together with this Twistor complex structure is Kähler, then once you have the Kähler condition, you have the Hosch decomposition. So then H2 consists of H11 of the small Twistor space. You already assume that Kähler, so there is at least the Kähler class inside, so it's non-trivial. And therefore, H11 would contain some rational classes. Therefore, it is projective. And we know that every closed analytic subvariety of a projective variety is projective. But then every single fiber of any Twistor family would be projective. And this would be a direct contradiction with Fujiti's result, which we know that not every fiber of a Twistor space is projective. And then we get a contradiction. Therefore, if you take the small Twistor space together with the tautological Twistor complex structure, it's not Kähler. And so on the differentiable manifold, which is the product of a compact hyperkähler together with CP1, we produce a Kähler complex structure, which is the product complex structure. And then we also produce a non-Kähler complex structure, which is the Twistor complex structure. And this answers an old question of Sir Michael Atiyah in every possible complex dimension. And thank you for your attention.